subwoofer, right? Right? So if Ka is very large, in other words, a subwoofer case, the sound radiates as if it is plane wave. That means to make a good subwoofer, Ka has to be very large. How to make a Ka large? Big. So that's why subwoofer is usually large. Alternative way to make a subwoofer, what would be? Maybe we make U0 is very large, which I will explain later. So that means I make a small subwoofer, but make a big stroke. So that it has the same volume velocity as this. Okay? This certainly indicates how to design the speaker. Maybe I generalized too much. Maybe one of the students, he said, hey, you only consider the very ideal case, breathing sphere, or how can you try to explain the radiation from speaker? Obviously, speaker cannot be considered as a breathing sphere. But then I can say that, hey, suppose you have half shell, and that is oscillating. And I can at least say that the sound radiating from the half shell in free space would resemble the sound radiating from the breathing sphere in only this direction. Or I can argue that if the wavelength is greater than A, or comparable size, then doesn't really matter whether it has this shape or that shape and so on, as long as we get the sound field in a far field. Right? In a far field, it looks the same. Okay. That explains the most of things that are okay. Next question is, what if I have two breathing spheres adjacent each other? Okay? What if I have three breathing spheres adjacent to each other? What if I have four breathing spheres adjacent to each other? Okay. We do have a solution, and considering that the governing equation is linear, therefore principle of superposition holds, therefore we can obtain the sound field that is generated by nth breathing sphere in space very easily. Okay? And then next question is, how about the sound field that is generated by trembling sphere? Which means that we have a sphere, but the sphere is oscillating. Okay. So that's the topic we are going to study in the next lecture. And the summary of today's lecture is the following. Any sound field that is induced by three-dimensional impedance mismatch, it can be considered as blocked pressure field and the radiation of obstacles in space, right? And the radiation of general shape can be understood by understanding the radiation from breathing and the trembling sphere. Therefore, we start with studying the sound radiation from breathing sphere, and we found very similar behavior that we studied for monopole sound source. Far field, near field concept, reactive term concept, resistive term concept, and also we do have a scale KR that measures how far from the origin. And 100 meter does not have any meaning to us. We have a meaning how far from the origin by measuring KR. And also we found the equivalent driving point impedance concept for the breathing sphere. The driving point impedance for the breathing sphere has a real term is proportional to Ka square divided by 1 plus Ka square, and imaginary term, the magnitude is Ka over 1 plus Ka square, similar with what we observed for monopole case. Okay, so now you see everything in terms of breathing sphere now. When I shout, woo, and you will see the many breathing sphere around his head, right? When I shout over here, many breathing sphere around here, right? Reason is we are handling linear acoustics. The beauty of linearity is principle of superposition holds. Any sound radiated from this can be approximated by using many breathing sphere. Now you can see breathing sphere, right? Okay? So let's continue to study about the sound radiation from traveling sphere, because the radiation is closely related with the scattering, diffraction, everything, right? Blocked frequency from and the radiation. This is not easy concept, but I hope you can understand this concept integrated way, not separated way. So everything what we have been learning is interpreted by using impedance. So what I call this acoustics, impedance acoustics. Okay? So let's continue to study impedance acoustics.